So a lot of times we hear about radioactivity, and one of the things that's nice about the nuclear chemistry is we talk about how not all radioactivity is as harmful as people realize. And in section 4.1, we kind of revisit isotopes to talk about some natural radioactivity. Does anyone remember what the isotopes, what that meant, or what an isotope is? That's actually a good review for the final.
It had a different number. It had multiple.
Different number of neutrons.
Yes, so it was considered the same element, because remember, the element is identified by the atomic number. So I could have, let's say, like hydrogen, 1,1, hydrogen, deuterium, and hydrogen, what's referred to as tritium. So all of these elements are considered hydrogen because they have an atomic number of 1. What does that mean? Their number of protons is the same. And it's the atomic number, the number of protons, that determines what the element is. The difference is their mass number, okay? And their mass number is the contribution of the number of protons plus the number of neutrons. So the reason why they're different is what was said earlier, is they have a different number of neutrons. So they're still the same element. Why? They all have the atomic number of 1, but they're isotopes because they have different mass numbers, because in the nucleus they have different number of neutrons. So here's, some examples. So radioactive isotopes are basically nuclei that are unstable. And because they're unstable, they try to stabilize by shooting out what we consider as radioactivity. And radioactivity are basically small particles shooting out at high speeds. So some of the radioactive isotopes that we can talk about are, we see right here, magnesium 23, 27, but magnesium 24 is pretty stable. It doesn't shoot out the radioactivity. But these all do, okay? And we notice that some emit radiation to stabilize. And in the case, you could have either one or more of the isotopes being radioactive. So a radioactive isotope is just one that's unstable, that's going to emit some form of radiation, some particle from the nucleus to stabilize. So there's different types of emissions, right? There's different types of particles that are shot out of the nucleus to stabilize them. So nuclear radiation is a radiation emitted by an unstable atom. And a lot of students have heard a lot about these. So one example is, you might have heard of an alpha particle. We talked about the alpha particles when I discussed atomic models and atomic theory, how Rutherford shot an alpha particle to a piece of gold foil, expecting it to always go through, but some of it scattered and shot back because it ran into the nucleus. Well, the alpha particle, which is written in a Greek symbol alpha, it's kind of like a helium nucleus. And the reason why it is it has 2 protons, and because its mass number is 4, if you take 4 and subtract the 2 protons, it has 2 neutrons. So an alpha particle is 2 protons and 2 neutrons, essentially. And the nuclei, when they're really unstable and they have to shoot out a lot of the mass out of their unstable nucleus, a good way to do that is to shoot out an alpha particle, okay? Now, we've already kind of discussed protons and neutrons, so you guys are familiar with that. The gamma ray, it's not actually, it doesn't have mass. It's electromagnetic radiation. It's in the form of light, and we talked about how light, it's not really a particle, but it does have wave-particle duality in the sense that it behaves like a particle and has energy, but it doesn't really have mass. So that's and we'll see that the gamma particle, the gamma ray, is the most harmful of the radiations. So we have talked about this when we discussed the electromagnetic radiation, and we talked about how the gamma rays were the most energetic because they had the smallest wavelengths. And these are, sometimes seen shooting out on their own from unstable nucleus, or sometimes a gamma ray will couple a beta particle emission as well. So a beta particle is interesting. It's basically almost like shooting out an electron. And the way it does that is you see that a proton or a neutron is converted to a proton, and it shoots out the negative charge to balance it out. And then the positron is basically a proton converting to a neutron and shooting out the positive charge it's like an electron size, but it has a positive charge. And the reason why you see the beta and positron breakdown is they're trying to get the number of neutrons and protons equal. They're trying to get that sweet spot of where you have the same amount of protons and neutrons. Alpha particle decay is just a quick way to reduce the mass of the nucleus. This is where I'm trying to get, the number of protons equal to the number of neutrons in those beta and positron emissions. So we're going to talk a little bit about each. So first, the alpha particle. And like I was saying earlier, it's 2 protons and 2 neutrons. So a lot of times they write it as, helium, because, helium has a mass number of 4 on average, and it has 2 protons. So here we see that. And the beta particle emission is actually like a high-speed electron shooting out of the nucleus. So it's much smaller. The beta particle is much smaller than the alpha. The positron, it's like the size of an electron, but it has a positive charge. Okay, so a lot of times they write this beta positive symbol because the beta, they use the Greek that Greek symbol for beta. And then the gamma, you see, is denoted as this symbol here. So one of the things in this class is we talk about radiation and how you can protect yourself. What I usually tell students is, for radiation, and it goes kind of back to our discussion when we first talked in chapter 3 about electromagnetic radiation, is the size of the particle, right? The size of the particle, you want to think about the distance it can travel. And then you also want to see its ability to penetrate through organic material. Okay. So typically what it is the smaller the particle, the further it can travel and faster, and the more it can penetrate. So typically the smaller particles are more harmful than the larger particles. So like the alpha particle is the largest of all the radiations. Again, it's like 2 protons, 2 neutrons. That's huge. The beta particle is the size of an electron, which is like 1/2000th of just 1 neutron. So the alpha particle is really big. It's a big particle. So as a result, it doesn't travel very far because as it's going through the air, it's so big, it has a greater probability of colliding into a particle in the air and falling down, okay? So it's really big, it doesn't travel as far, and as a result, it doesn't penetrate your body as much. So because it's so big, we can use a lot of things that are simple to protect us. Paper. A piece of paper will protect you from an alpha particle. Your basic clothing that you wear will protect you. Now, when you have smaller particles, like beta and positron particles, which are the size of an electron, now they're a little bit smaller. And as they're smaller, they're going to travel faster and farther, and they're going to be able to penetrate your body more. So you need to have a little more protection. So what would that entail? A heavy lab coat, so really heavy material. Maybe a thin sheet of, aluminum foil, or just a thin sheet of metal. You can see this person right here, this is called the shield. So a lot of times thick plastic shields or a glass shield. You can also, like the mask that welders use, you can use those types of face shields. to protect you from beta particles. Now, if you're talking gamma, okay, remember gamma is just a photon of light, and it's extremely small. So for that, that's a little more serious. You need something like lead that's really dense, or thick concrete, right? So I had even talked about, when we discussed electromagnetic radiation, X-rays are right next to the gamma rays in that spectrum. They're not as small as gamma rays, so they don't travel as far or as fast, or they actually travel the same speed, but they don't travel as far. But, you know, when you go get an X-ray, one of the things you put on is that lead apron. And why is that? Because the X-ray it's so small, its wavelength, it can penetrate your skin and go through your body. Well, it's the same thing with gamma. It's extremely harmful. So you have to really protect yourself. So limiting the amount of time spent near any radioactive source is, good, right? So you want to minimize the amount of exposure to radiation. And obviously, the further you are, the less likely it is to reach you, because the farther you are, the more likely it's going to collide with something in the atmosphere. So increasing your distance definitely improves your chances of it not reaching you or penetrating your skin. So one of the things that I want to emphasize right now for you not to worry about are these numbers, okay? So for the shielding of I don't expect anyone to remember these numbers. I'm just bringing this up because it just emphasizes what I was basically saying. You want to think relative size, distance of travel, and ability to penetrate into tissue, okay? You don't need to know the exact numbers, okay? I don't want anyone to think I'm going to test you on that. Now, this relationship that I'm talking about, you should be able to understand that. So the alpha particle is the biggest, so it travels the least distance, only 2 to 4 centimeters. Beta particles are smaller, they can travel 2 to 300 centimeters. Gamma particles are extremely short in wavelength, they can travel 500 meters. So again, the size dictates the distance of travel. So the bigger it is, the less it travels. Then when we look at the penetration aspect, right? The tissue depth, the alpha particle only 0.05 millimeters of skin. So that's in the upper epidermis layers, okay? Beta particles can go a little bit deeper, and then gamma, well, shoot, 50 centimeters, that's quite a bit. What is that, like 20 inches? That's like 20 inches. So it's like, through your body. So the gamma particle, which is extremely small, that can travel very far, has the most penetration. So as a result, what could you do to protect yourself? Well, you can shield yourself. So we already talked, the bigger ones, paper. The really small ones, now I need dense material like lead and concrete. And then in the middle, heavy clothing, lab coats, things of that nature. So again, we do need to memorize specific numbers. What we do need to understand is the relationship of size to distance to shielding.